Computer graphics heavily depends on transformation to create dynamic, realistic, and interactive visual content. Rotation is one of the fundamental types of transformation alongside with translation and scaling. In two-dimensional graphics, objects are rotated around a fixed point, often to the origin of the coordinate system. The rotation is at two axes, x and y. In three-dimensional graphics, rotation are more complex. The rotation can occur about any axis of x, y, or z. Rotational transformations are vital for creating dynamic and realistic graphics, from rotating two-dimensional sprites to handling complex 3D-dimensional rotation with quaternions. Understanding how to apply rotational motion is key to modern computer graphics and interactive visual applications.
So for the shape, solid is fixed and does not change unless force is applied. For volume, it's constant and regardless of the container. For the molecular structure, particles are closely packed in a fixed organized arrangement, lattice. For movement, particles vibrate in places but do not move freely. Example, ice, metal, wood, and nougat in its solid form. For fluid is liquid and gaseous substance that can flow and take the shape of their container. For property, fluid adapt to shape of the container. Volume, liquid have a definite volume, gases expand to fill the entire container. Molecular structure, particles are less tightly packed compared to solid. They are either loosely packed liquid or widely spaced gases. Movement, particles move freely and slightly past each other. In liquid, they move at a higher speed in gases. For example, water, air, and molten nougat in its fluid state. So for application in biotechnology, solid are used for chromatography and separation. Solid resin matrices are used in chromatography column to purify biomolecules like protein, DNA, and enzyme. Bioreactor components, solid support like microcarrier are used in cell culture for encourage dependent cell. Membrane are used in filtration and separation process. For next is diagnostic. Solid substance like glass slide and microarray are used for detecting biomolecule in diagnostic tests. Example, DNA chips and ELISA plate. For last part for application in biotechnology, fluid are used in cell culture and growth media. Fluid like liquid growth media are essential for culturing microorganisms, animal cell, and plant cell. Drug formulation, injectable fluid like saline solution are used for delivering drug and vaccine. Next is cryopreservation. Liquid nitrogen is used for preserving biological sample like cell tissue and embryos.
Now I will explain to you the concept of thermal physics and the application in biotechnology. Thermal physics in simple terms is the study of temperature and heat. The key areas include thermodynamics, theory of kinetics, and statistical mechanics. One of the application of thermal physics in biotechnology is bioreactor. Bioreactor is a type of fermentation vessels that provide an ideal environment for cells to grow and proliferate. We use bioreactors since it can be made specifically to fulfill the growth requirement of the organisms that we choose. It then transforms the biological base materials from these organisms into products like enzymes or other biocatalysts. Thermal physics is applied in bioreactor through thermoregulations. Highly proliferative cell is very sensitive to temperature, so we need to precisely control the temperature in this bioreactor. Too high or too low temperature can lead to reduced efficiency of production, denature the enzymes produced, and even lead to cell death, which means we need to start all over again. Meanwhile, maintaining ideal temperature range will maximize our production yield and ensure the production is only of high quality. Thermoregulation include heating and cooling systems, temperature controllers, and thermal insulation. These are the type of bioreactors that is available now, and these are some of the important applications of bioreactors.
The law of thermodynamics and its application in everyday life. Okay, so the first law stated that the energy of the universe remains the same. So even though the energy may be exchanged between the system and its surroundings, it cannot be created or destroyed. It redefines the conservation of energy concept. An example for this law is pouring water on a stove. Next, the second law stated that heat flows spontaneously from a substance at a higher temperature to a substance at a lower temperature, and it does not flow spontaneously in the reverse direction. So, any spontaneously occurring process will always lead to an escalation in the entropy of the universe. An example for the second law is melting ice. The third law stated that the entropy of a perfect crystal at a temperature of 0 Kelvin is equal to 0. At absolute 0, entropy approaches a minimum constant value. An example for the third law is cryopreservation. So, what is cryopreservation? It is a long-term preservation of the biological materials at sub-zero temperature, where all the metabolic activities are arrested, keeping its viability intact to be used in the future. What is the connection between the laws of thermodynamics with cryopreservation? As the temperatures approach extremely low values, the molecular motion starts to slow down significantly, minimizing entropy and preventing degradation of the cells. The importance of cryopreservation in biotechnology is preservation of valuable biological samples, ways to support the research and development, and for the long-term backup of future use.